Hi, this is the presentation I did in 2017 for a Brazilian symposium called SNPTEE, in which I talked about the partnership between Chesf and RNP. This partnership consists in the creation of a backbone based in ROADM, what I start just calling as ROADM, and its access network based in SDH over the same optical cables. First, let's talk about RNP, which is a non-profit social organization that manages a huge telecommunications network with the goal of connecting several universities, federal institutions, hospitals, laboratories, schools, and so on, between themselves and to the internet. In 2017, RNP had about 800 links contracted from telecommunications carriers, and to afford that, it used to count with an annual budget of 250 million Brazilian reais. In the picture, you can have an idea of the IP network. In that time, the link with the highest throughput was 20 gigabits per second. Just a curiosity, in Portuguese, I sounds like E and P sounds like P. So, Brazilians say IP when they want to talk about the Internet Protocol, which sounds exactly like a Brazilian tree which named this network. And what RNP was expecting for 2022? Nowadays, a telecommunications carrier called Oi provides several links to RNP due a kind of agreement with the government, which will come to an end in 2021. As responsible for the communication between Fortaleza and Porto Alegre in the Bela program, they must provide at least 100 gigabits per second between these two Brazilian cities. Beyond that, one upgrade is necessary to support the new client's needs. So, to overcome the end of Oi agreement and improve the IP network in order to deliver the desired throughput to its clients, RNP started to think about creating partnerships with carriers and utility companies. And now let's talk about Chess, the company I used to work. In this slide, you can see some characteristics about the company's telecommunications infrastructure. In this picture, which is from the Power Transmission Operations Center. What is important in this context is highlighted in red, almost 9 kilometers of OPGW cables, which stands for Optical Ground Wire Cables. Basically, is a ground wire for power transmission lines with optical fibers in its core. So, as you see, Chess had the cables and the OEM expertise, and RNP had the money to buy all the equipment. This is the kernel of the partnership. RNP provides all the software, hardware, and training, while Chess provides the optical cables, operate and maintain the system. Once both companies saw the potential of this partnership for their own business, now it's time to plan a solution which fulfill both companies' requirements. However, each company has their own priorities. RNP was focusing in scalability, throughput, a future-proof technology, and reduction of O&M costs. On the other hand, Chesf was worried in reliability, switching time, and compatibility with old devices such as routers and SDH working over STM1. Before we start talking about the solution itself, let's understand the evolution of WDM. This image represents four sites connected by optical cables in a physical ring topology. Use the old-fashioned DWDM architecture that Chess had in its plant. So what we can see here. First, you can tune the transponders. It means that if you want to work with 20 channels, you will need 20 different kinds of transponders, which demands at least the same number of transponders in your spare to allow the maintenance team to change the measured one as soon as a problem appears in the system. Second, it has a fixed bandwidth of 50 gigahertz. So you can't reduce the bandwidth of channels to allow more services, and you can't also use super channels to transport services with high throughput. Third, despite of the ring topology, the communication is essentially point to point. For instance, to site A talk to site C, it's necessary a physical bypass in site B. And finally, if you need to change something in the configuration, like the channel of service, you must send a technical to the station. This is necessary because this system is not smart to allow remote management of the optical flow. And how the solution adopted in this partnership differs from the one I just presented you. Here you can freely tune your transponders, and when I say you can do it freely, it's not just because you can select a different channel of the ITUT standard table. With the Flex Grid feature, you can define any central frequency with any bandwidth, supporting more channels with lower capacity or less channels with more capacity if you want. So, instead of being limited to the standard DWDM table, your only restriction now is selecting frequencies inside the C-band in steps of 12.5 GHz. Moreover, now you don't have several point-to-point links, but an integrated system, creating a real network which allows the configuration of services to and from any node. And now, since you have all the necessary hardware deployed, you can change network configuration such as channel of the transponders or connection between transponders in different stations through the NOC. Here is the initial backbone proposal. ROADM technology using a pair of optical cables, coherent transponders, amplification system sized to support 40 channels, OSA and OTDR in all directions of all sites, including the ones that don't have ADM, and protected by WSON over about 6,500 kilometers of OPGW. Later you see that we changed this protection, and I will tell you why. And now let's see which challenge we had to face and how we overcame them. First, as I told you before, Chess have many old devices working at low rates. And as the minimal rate accepted in the ROADM system is 10 gigabits per second, we needed a solution to make the low rate clients reach the WDM layer. So we decided to use OTN as an intermediate layer, like a bridge between the existing hardware and the new backbone. And as we start counting with OTN, now we were able to protect the system with AZON instead of WZON, which was selected because of the switching time is much faster than WZON, and because does not demand standby regenerating transponders deployed over the network. Our second challenge was the number of optical fibers available. In some parts of the network, Chess had just 4 optical fibers, all in use with SDH links protected with MSP 1+1. So, what was the solution to take out 2 optical fibers of the existing SDH network without compromising the level of throughput and resilience? We changed the protection scheme to MSP ring, demanded just 2 optical fibers, and the line card rates for STM16. With this, we improved the system in both data transport capacity, because now we were able to transport 1.25 gigabits per second of protected services instead of just 622 megabits per second, and availability, because now a problem in the optical cable will affect just one circuit worker protection instead of both. To understand the MSP ring scheme, look at this picture. Here you can see 4 sites connected in a ring. The idea is provisioning half of its capacity with the services you want to transport and have the other half dedicated to protect the first one. So let's focus in the link between A and B. While there is no problem in the network, they are connecting each other directly. But when you have a problem between them, no matter if the problem is in a line card, cable, or any other element between both sides, the information in A will be sent to D through the reserved bandwidth between these two stations. Same way, this data will be transported from D to C and finally from C to B. Once the direct link is up again, A and B start to communicate to each other directly and the protected resource are once more available. Okay? Note, while this resource is not being used to transport protected services, it can be used to transport non-prioritized services. So, for instance, you can use this resource to provide a second one link between each side. So you can improve the network throughput while there is no problem in the system. This upgrade in the SDH network demanded the replacement of most of the SDH devices we had in the plant. The third challenge was a limitation of the MSP ring, which allows just 16 network elements in a ring, while Chess had some physical rings with more than 30 elements. To work around this limitation, we decide to split a huge physical ring in some logical rings. So how it works? Look at this picture where we have 4 sites connected in line. 2 fibers are dedicated to connect the SDH devices, and other 2 fibers of the very same cable are used to connect OTN device. I represented them as the line red for the SDH and the line green for the OTN. Here you have SDH in all 4 sites, but you have OTN just in sites A and D. B and C are just bypassing the signal. You also have a connection between the SDH and the OTN in sites A and D. Okay? To create a logical ring, to make feasible the use of MSP ring, you will use the same strategy between A and B, B and C and D, okay? So how we will connect D to A in order to close the ring? We will transport this link over the OTN. So for the SDH layer, this is a ring and works exactly like the physical link you saw 2 slides before. So maybe you think, yeah, but if you have a problem in the cable, you have link down between A and D and between any other 2 sides. So the ring will break in 2 points and services will not be able to transport. It would be true if we don't have the backbone protected, but the ASIN will avoid it, and I will show you how it will work in the next slide. So this is the topology of both SDH-based access network and the ROADM-based backbone. The blue circles represent sites with SDH and amplification for the backbone, and the square represents sites with both SDH and ROADM with OTN. Let's focus in this logical ring between FTZ and PAF, more specifically in a service between BNB and MLG. If you have a problem in any element between these 2 sites, for instance, if you lose the site in which there is a logical bypass of the SFC, the MSP ring will start sending the SFC to the opposite direction. The OTN layer will provide the bridge between FTZ and path, and the data will be delivered to its destination. Once the problem is solved, the network returns to the normal state. Now, what will happen when you have a problem that affects all fibers of the OPGW? The MSP ring will run, delivering the data to the SDH connected to an OTN, and as this OTN can't connect directly with the remote OTN, the ASON will provide a path between these two sites using the available resource in just 50 milliseconds. And what happens if, before the problem is solved, another one appears affecting this new route? Since you have resource available and the OTU is protected as a diamond service, another path will be provided and the service will be switched to this new route in the same 20 milliseconds. So you can see that we start from some premises, and during the planning phase of the network, we improved its features. Instead of the 1 minute that we was expecting from the W zone, we had 50 milliseconds of the A zone. And the final solution become even more reliable than the initial configuration. Thank you very much for your attention. And if you have any doubt or want to talk about the project, about some details of the solution, whatever, here you can see my contacts. You can email or you can call me. Okay? Once more, thank you very much.